saying is, I'm sorry to doubt you, but maybe it's your program that's just not doing anything.
We submitted 11:59. There's one guy that does
Can I just suggest what you need to do is either take one of the programs from WebAssignment 1 or my little test tool and try and run that. Just try and run the program you know works, and then we can decide whether the hardware works or not. At the moment, we don't know whether it's your board or the hardware. So does your program run on the boards? You've got to get into the mindset of fault finding. The first thing you do is work out whether it's your program or the board. So the simplest thing to do then is take the program you know works, then try it. If it doesn't work, then we go board stop. I'm going to tell you what to do, suggest what you do. But before you do it, I would really ask you to run very simple test program, just to confirm. So when you ask this question by Malcolm Bailey, you can actually answer it. So, each game's program to my own programs that I wrote earlier, just to moving on to that. So you do that test, you're sure the build doesn't work, you then go to SAC 31 and SAC build. C31 is the SAC build building. You go from Granby Rail entrance onto seat floor, go straight ahead out the stairs, it's about halfway down on the right, left. Go in there, ask for Malcolm Bailey, who's the chief technician, and tell him your board doesn't work, so he should come and ask you what to do. He will take a look at it and decide how bad the problem is. He will then probably suggest go to the electronics team next Wednesday and get some help fixing it. Malcolm will want to know and try, we've actually just demonstrated the board doesn't work by just running the program that you know definitely works. You'll just ask him the same questions. Go to C31 now. But please try the program first. But once you've done that, the days afternoon, they usually work for the mate from about 8 in the morning until 4 in the afternoon, so it's getting close to 4 o'clock. But you know, if you don't do it now, you don't watch it. You don't do it soon. You can actually just drop in and have a chat. It's a very nice guy. Really.
We did run and teach him after. Victoria Hall. How was everything? How was it? Alright. Excellent. Yeah. Second year.
Another demonstrator told me that my program is only a little wrong because it's just
Nothing about the yeah.
which means
Keep getting better. And how's
scores and so he urges me to send to email.
I need to know which demonstrators we're talking about, because then I need to go and have a talk to them.
What's the question? Yeah, I missed
Well, there's two Chinese lads, one's PP and one's Chow. PP is very slim and quite tall. Chow's kind of sort of the tall guy. So he wasn't there yesterday. PP wasn't there yesterday. So there's... He was not, the tall, slim Chinese guy was not demonstrating yesterday. Well, you need to send an email about it.
Yeah, absolutely.
I don't remember an email about this at all. And I've read all my...
I did it yesterday, right after.
Can you resend an email to me, please? Because I don't remember seeing it. Was it? Did you have your program attached to the email?
Yeah.
Oh,
No,
right.
not attached. In the email.
Yeah, I just filed it from the thought it was a program. So please send it to me, then I'll read it carefully, and then I will try and find the demonstrations. I'll talk to them, I'll talk to you again. Right, who's today?
Jessica? I was going to say that you said you wanted to speak to me.
So, yeah.
Yes, I'm on time.
So, we do you right. Right, yes. Swiss electronics. It's great. That's what you do.
Is it?
Yeah, absolutely.
I don't know what to do.
Well, do what you like, and I mean that. I mean that in the true sense of the word. Doing things that you like will make you happy.
Everything sounds good.
Can we just go outside? 'Cause I think it's mine. It's mine.
Hello? Is Andy there? Can you transfer me? Hey, bud. I'm just in the middle of class, don't worry. You can hear the hubbub behind me, but they're not actually paying attention at the moment. Sorry, I'm just trying to log in. Seems my brain's not able to cope talking and writing the password in at the same time. I know. Can you find out if Reynolds C... Hello. Oh, is he? 3 till 5. C16's not available though. Oh, right, okay, so we can't say where we are. That was the next question. Right, I went up to the room. All right, well, no problem. Thank you for trying. I am. Okay, well, I'll put you on voice so I can start doing that. I'm working hard on your behalf here. Hello. All right. Thanks for trying. Yeah, thank you for trying. Okay, everybody. Sorry about that. I can get the rooms upstairs next week, but I can't get it this week, and it just started raining outside. And no, this room's not free, and next door's got Simon Ferrier and the C16's got somebody in. So we're going to have to, those of you keen, budding souls who really want to do run cutter and do one of the exam questions that's been on a few exam papers, we'll walk down the road in the pouring rain to James Chadwick along with my lovely demonstrators who will turn up this week. Or else. Okay? So, sorry about that. I tried really hard. I can't do anything. I've been upstairs just now. That's why I'm 5 minutes late. Just to check the room, and the guys who were camped in D2 were actually telling me that the drilling had been going on in the morning in the room next door. So I actually thought I was going to do what I told me. All right. So, to commence, welcome all. So that was where we left it on differential reactor. So let's just have a look at the setup of the differential reactor and just make sure we know that the first equation is the straightforward flow reaction equation. Obviously, and it will be, the question will be in your minds, or it should be in your minds, is where the hell is all the particle stuff that we're talking about? Of course, it's wrapped into your rate constant, because your rate constant will now have your TV modulus stroke effectiveness factor. It'll have the surface area of the structure, and it'll have the actual density of the structure, because if it hasn't, it means you'll have the wrong amount of catalyst in your tube, etc., etc. So you've got to remember that that function there contains the bit that is new. So differential reactors have a big advantage because the smaller the change, the more you can just do the straightforward kind of Simpson's rule type approach that you use for numerical methods, where you've got a very small change in conversion, so you can do a numerical difference between the last segment and the next segment, and the overall area will approximate the integral. So it allows you to do a simple calc in small steps. For those of you who weren't here this morning, remember that if you are setting up any kind of design on an Excel spreadsheet, don't do it in 100 increments. Do it in 10 increments so you can see the mistakes propagated on the page. So that was just a tip, which is long experience that engineers love overcomplicating everything. So the advantage of the differential reactor is, should you get a straight line plot, you know it's first order. Your small changes probably mean that your x's on the data line will actually be nearer the data line because you're looking at very small changes, so you should be able to spot them. So your x's, your data points, will actually lie better at low conversion because you'll have less secondary reactions. You'll have less complication. Main disadvantages, well, you're measuring really small changes in composition, so now you've got an error on how good your machine is to do that. You're very lucky if it's gas phase and you're in the oil and gas business, because gas chromatographs, which I've worked with for donkey's years, have a large dynamic range and are very sensitive, so that's okay. But if you're in a liquid phase catalysis, or you're doing something that's got a poor separation technique, you're really struggling to measure small changes. Remember what that means. You're putting in a large amount, you're not converting very much, so you've got your large amount going through with a little bit of converted, and you're measuring a very small difference. That's what that means. So that small bit gets ever so slightly bigger, so you've got major problems, potentially, on the composition. Exam question, starter for 3 marks or 4 marks. Okay, that's what you're looking at there, and that's why the description's written beautifully. That would be the model answer. I'm not saying it's on the exam paper, as you know, everything's on the exam paper. But that's sort of what I'm looking for the marks. I'm looking for the advantages, the disadvantages, and maybe something about it. You're testing for linearity. You know how to do that when you're plotting against orders. So first order, second order, you've got a test for a first order and a second order reaction. That's basic kinetics, first year and second year CRE2. Key things are if there's small changes, small conversion, very low thermal effects. If there's very low thermal effects, then there's very good chance of getting good data. And your rate data is directly calculated or got from the data when you plot the rate against concentration. Small thermal effects, small compositional changes, a very delicate way of trying to get at the very early kinetics. What does it mean to you as engineers? When you've got that paper in front of you, you're looking at what conversions are they looking at. Not can I get rate data, which is some of your problems you've said already, but can I get rate data on very low conversions because it will give me the intrinsic kinetics that are on the reaction. That's what you're looking for. If you've got something that's a 500 degrees C that gives you 80% conversion and they're worried about this, that and the other, you're not really getting kinetics. And your next question is it actually at the thermodynamic equilibrium? If it's at the thermodynamic equilibrium, you can't get kinetics anyway. Because you're changing the temperature to change what's happening, but it's all as at equilibrium, it's always at equilibrium. So you can own, this one is a real sure and fast way. The problem is not many people do studies like that, therefore there's not that much data available. If your project is oil and gas flavour, if it's going to talk, and some of those are going to talk, about standard processes such as shift reactions and stuff like that, you have a lot of data you can get at. Somebody asked me about what books you might get kinetic data for before. There's another book that you might use, which young Tom has. So the Catalyst Handbook, which is by Martin Twigg, might help you with some of your kinetics and some of your processes that you're designing. Okay, it's a really good book. Those who were here before saw that Yours was a good book. YAWS, Yours, was a good book for basic thermodynamic data on lots of things. Perry has some information. Yours may even be online. I don't know if anybody looked in the break because you were probably doing other things, but have a look to see what you can get online for Yours. YAWS is the surname. It's a classic text. It's like a Bible of thermodynamic data. Anybody in industry goes straight to that for the data first. Okay? Right. So what's an integral reactor? Well, it's just a posh way of saying the conversion is generally greater than 10 or 20%. I've been doing this bloody job for years. And 10% is usually the rule of thumb I apply, but sometimes people say 20%, so it's up to you. Anything greater than 10%, and I'm not sure, I've not got secondary reactions and side reactions, so I normally use 10. But if you see written 20, it's fine. It's just my experience is saying 10, not 20. So the integral equation is there. So now you've got a problem because you've got an integral function on the side. You're not just looking at small changes, you're looking at big changes. The chances are that if you try and plot it and you're trying for a linearity plot, all it'll tell you is that if you've got a curve, it's not doing what you think it is. So that looks a bit confusing, that graph. So imagine that you've just got the one line and you've plotted the data, and imagine the data fits on the curve. So you've plotted what you think is your model. It's a straight line plot, but your data is actually a curve. What do? No, you don't take a log-log plot. Okay, to try and make it straight, what you do is you go, I've got the wrong model and start again. So you go, it's not first order, it's second order. So you change the model to do your basic calculation. I'm hoping that you remember that a first order model is log of 1 over 1 minus x, and a second order model is a change of 1 over concentration, so go back if you don't remember what it is. I'm not going to ask you to remember it, but you do need it when you do design. Okay? So the main advantages and disadvantages, well, obviously, if you've got high conversion and it's got any energetics at all, it's going to have thermal gradients. the reaction is likely not to be isothermal. What a helpful little prop. For those of you who want your posters back, and I know two groups or one group did, I couldn't find it in the mess in my office, so if somebody wants to pop by next week in the spare hour, we can have a search through them together for whatever group it was. I think it was either 16 or 18, I can't remember which group wanted their posters back. 16, 18 and 19 wanted something, I remember that much, but remind me. So if this is your reactor, which is not too unlike a reactor that you might have in industry, a pilot reactor, my reactors are half the diameter of that, so that's what actually, that's a bit more, well, it's a bit more than an inch across, but mine are about ½ inch. So that's roughly the length of them, and the catalyst will sit in about here, and all this will be heated, or you might put the catalyst in the middle. Okay, so that's roughly what it looks like. It can bring you in a stainless steel tube, it'll look just as exciting as that, but it'll be a bit smaller. But it gives you the length scale, it gives you that the catalyst I'm testing is about 1 gram. In this case, you'd probably say I can put about 5 grams in, but if we scale it down, that'll be 1 gram. The bed depth will be about the size of the first digit on your thumb. So about that. So it'll be in there. So your heat is piling in from the outside, and the temperature inside your reactor is likely not to be at the set point. Do you understand what I mean? It sounded easy. Did you understand what I mean? I'm going to assume silence is you want a bit more explanation. So it's not very straight. And over there, I hope you can see it. I tried to make it big. So let's put the catalyst in here. Let's have our liquid and our gas feeds. Let's say it all vaporizes, so it's gas going through there and our products are coming out there. This is where the catalyst is. And this is a plot of temperature down the reactor. Temperature equals conversion, depending whether it's an endothermic or an exothermic reaction. Depends what you're getting. Temperature equals conversion. So if the temperature should be, okay, so that's the set point. The set point being here. Top, bottom. Now let's draw the catalyst in. Put the catalyst there. Same graph, I've just drawn it this way to put the temperature. So now your set point is here. And it's 400 degrees C. Because Dr. Garforth put it in his paper and said that's what we set the temperature to. You're reading my paper, it says 400 degrees C. You have absolutely no evidence that that is correct. First you have common sense. Common sense says what's the delta H of this reaction? Has it got a negative sign? Is it 10? Is it 100? Is it plus? Is it 10? Is it 100? Okay, let's get rid of that now. Is it 10 kilojoules per mole? Okay, so that's it. That's what we discussed this morning very briefly. You didn't necessarily catch it all, so let's do it very quickly again. That was around parametric sensitivity. So if we've got this one, we've got a big exotherm, it's going to heat up a lot. This one, we've got a big endotherm, it's going to cool down a lot. So, I'm going to give you the real temperatures of a real reaction. Okay, so this is a dehydrogenation reaction. Okay, to produce hydrogen for an exhaust, for an engine that goes into a car. So we're producing hydrogen. It has an endotherm of plus 200 kilojoules per mole. So it's very endothermic. The bed depth is no bigger than your thumb. In fact, actually, the black top on that pen is a better representation. It's no bigger than that. I've got a big, chunky, manly-sized Yorkie heating furnace putting the energy in all the way from top to bottom. What's your temperature drop? Just on that bit of catalyst. Remember that? It's bigger than that scale, and we're bringing it down half again. So I think trying not to hit the microphone. Any ideas what the temperature will actually be in the reacting zone? I'll make that a little bit bigger for us so we can exaggerate it. So what's going to happen when we put our feed over the catalyst? Is it going to be all at the same temperature? The temperature will drop. So we're now feeding it in. Okay, maybe the best thing is to use a red pen. notepad, which I left in my office. Brilliant. So let's say this is the top of the furnace. So we're putting it in. Here's the tube. All right, maybe I should have started it there so it lines up with the tube. So it starts off, and it'll be lower. Okay? Okay, because we're putting in a cold feed, which we haven't warmed up, liquid or gas or both, and vaporized it. So we're going to start off a bit colder. Then we hope we reach the set point. Then we've hit the catalyst bed. Now it's doing a very endothermic reaction. Can you see okay over there? It's probably a bit of a mystery. I thought you were going to say no. Okay, I'll draw it over there again. Can you see now? Better? No, it's a long way away. Okay, so it's reaching the temperature. It now hits the bed. What happens now? It's endothermic. It's going to go down, right? Because it's cool. It's cooling the reaction. But how much is it going to go down? That's 370. Okay, let's say that's 320. Let's say that's 270. Okay? It's only a gram of catalyst. It's only in... Sorry, I've lost my reactor. There we go. It's only in the top. Alright? Any ideas? Would you, and it's a guess, would you say 10 degrees? Would you say 20 degrees? Would you say 50? Would you say 100? Would you say 200? What would you say? Any idea? Any concept after this morning's discussion on the explosion? He's re-evaluating that guess now. Yes, I thought he might. It's cooling, remember, so he's not going to blow up. So go with your guess. What were you going to say? 70. 70. Not a bad guess. Higher or lower? Higher. Ooh, it's a split decision. The lower was very confident. It is actually lower. Okay? So it drops down to 270, and then as the reaction starts to pick up, as the reaction exits, as the reactants exit, then the heat is being put in. So you've actually got a real temperature drop minus 100 degrees C. And that's in the best reactor I can make, with the best injection of heat that I can put. And I'm giving you scientific papers with that error built into it. Difference between my papers and quite a lot of people's papers is I've got a thermocouple in the middle, and I can tell you that. So then you can try to model it. Of course, you want it to be isothermal because that makes your model a bit easier. But what happens is the reactant hits the catalyst, it drops so quickly, it's actually adiabatic because the heat can't get through into the reactor enough, so it drops until it reaches a point where the furnace can start to compensate for the heat that's being lost. And then it's isothermal, and then it's off warming up because it's now come out of the reactor. And that's what happens in your reactors when they're a bit bigger as well. Except you've got this heat that might be generating. So now maybe if you believe me, and I can bring the reactor in to show you, but if you just imagine that the total bed depth is no bigger than the cap on that pen, and I've got a furnace that's piling in heat like your oven cooking at home, and it won't warm up the central core better than 100 below the set point. You then scale your reactor based on that. Okay? So that is the problem, and it's constantly a problem if it's an exothermic reaction that you end up being on that. So what's happening basically to this side of the room is the temperature warms up to the set point. That's what you hope to have, what you have because you've got cold feed. You then get to the reacting zone, it drops, comes hurtling down until it may be a bit isothermal, and then you exit the reactor and it starts to warm up, and then your product come out. The catalyst is in that bit there, and that's temperature, and that's minus 100 degrees C on 340 degrees C in. And if you're not surprised by that, I guarantee that any chemist that you put that to will A, not know that, and B, not expect that. Because you have to check that the chemists have been working on the process and understand that their reaction temperature is not what the set point is. If they just tell you what the set point is, they're telling you nothing. Good news is that engineers, of course, have brilliant packages which tell you all about that, and you can start to model it. But go on.
So the temperature decreases because the reactant comes in contact.
So the reactant comes in, it hits your active sites, it does its job, It starts to convert it, and every mole that's converted cools, takes heat away from you.
And then when the furnace gets...
So now it gets to a point where it drops to 270, and at 270 the rate has slowed so much now, because you're 100 degrees cooler, that now the furnace can start to balance the energy that's being taken out by the reaction. Is then balanced by the thing that you're putting it in with. So you remember you've calculated UA delta T's. You've started to think about the energy that you need to cool or to heat something by. This is what this is talking about. It's saying that this reactor cannot supply the UA delta T term, can't give you enough warmth to keep the temperature at your set point, and it automatically falls to this point here.
So what's the solution?
There is no solution. Well, there's a part solution, because engineers are quite canny little devils when they want to be. You can split the reactor, but if my reactor is only the size of my thumbnail, we're a bit stuck when we come to a meter cubed. So what you do is you do multiple tube reactors. So that's why you see multiple tube reactors, to try get the heat out or put the heat in. So that's why you'll have a long reactor. So you'll say, I need 1 meter cube, but I'm going to split it into 7 or 10 columns of 7 and 10 reactors, which are thinner and allowing you more heat in. And that's all you can do. Or you can control the reaction so it's not as fast, so that you can slow it down. You dilute it. You add a diluent and you just cool the reaction down. So you're slowing it down. You effectively bring your set point nearer to the point where you can put enough heat in. Does that make sense? Yeah. Okay. Everybody else all right? Up. Yeah. Front row now. Yes. Go on. We've stimulated, so away we go.
Is there any way that we can, on that particular point, that we can provide more heat than the rest of the points, so that it's a bit, the difference is a bit less?
So there are ways to do it. You could imagine that temperature drop you can't do anything about. But what can you do? You can split the tube, so you make it thinner with more of them. Or you could put metal or something in it that's a better conducting. So you could dilute your catalyst with something that's conducting. That is done. You could maybe put your catalyst on something that's maybe metal, so that it allows heat conduction down it and convection, and then the catalyst that's around it has a much thinner layer so the heat gets into it. So those things are also done. But the diluent is the common way of slowing the reaction down. So when we talked about adding a diluent, that's what we meant. Okay? That's a side salad, if you like, to this area. But it does that the other way around. You can see that that reaction this morning was 100 degrees C. They only talked about rising the temperature 100 degrees C above where they wanted to be, and 40 degrees C away there was the secondary reaction and the whole thing went pop. Okay, killing people. And that's basically the reverse of that. So when you talked in CRE2 and did your heat integrations in CR2, that is actually what is happening in a real reactor. So, beware of high temperature gradients. There are other issues when you've got packing, and there's issues about mixing, and there's exit and entry mixing effects. So what does that mean? I've just drawn, there's 2 squiggly arrows for the ones on the right-hand side of the auditorium here on the top of it. One is meant to be a gas and one is meant to be a liquid. You're putting them in, and in some way you're mixing them at the top, and you're warming them up so that you get them there. But you're mixing a gas with a liquid. You're vaporizing the liquid as it enters the reactor. The gas and the liquid are mixed, hopefully, in some way, and then they pass to the catalyst, and then the reaction takes place, and then they pass out of the reactor. So any of that's not set up right, or you've got kinks in the system, or valves, or knobs, or bells and whistles, or anything, any bends, turns, twists, not appropriate pipe dimensions, and it's not going to be mixed. You've also got the problem that when you're passing it here, if you haven't got, what is the equation that we use for knowing the number of particles across the bed? Anybody remember? Okay. So the particles should be a tenth. Should be less than equal to. It's a tenth anyway. Since my brain is not as good on a Friday afternoon, let's say it's equal to a tenth or a 20th. Okay. So the particle size, to get enough particles across here to allow no channeling through. That's what you need. So remember that. Put that into your back pocket, and you're able to design things. But it's not something you're going to write in a textbook. It's something you're going to have picked up from the course, and then when you're designing it, you can now use it. But remember these basic things. Okay? Right. So, new reactor. Not really. You asked about what you can do with heat. And it was a very good and pertinent question. Here's one example. So instead of doing multiple tubes, you could have multiple levels. If you remember CRE2, and I'm sorry to the MSc students, I keep saying that, so hopefully you've got the booklets, but in CRE2 you will have found multiple tubes, you'll have split the bed like that, and you might put little heaters in between the beds to make it warm up, or you may put little cooling tubes to cool it down. So what happens is it goes in to the bed, and then something here takes heat, either puts heat in or takes heat out in between the beds. So it allows you to try to stabilize the temperature. And that's one of the things you would do to help control temperature. So a recycle reactor. What do we need to know about a recycle reactor? High recycle equals CSTR. CSTR equals number crunching. Everything else has got difficult integrals and difficult equations in. CSTR is just simple concentration at the beginning minus the concentration at the end divided by the rate equals W over F or whatever. So recycling in effect helps to mix. Recycling helps with thermal gradients, it helps with velocities, mixing, transferring of material. It helps to distribute the heat, so it helps reduce thermal effects. So you can incorporate heat exchange or heat cooling, well, heat exchange in or out, and you've got the various effects. So it's a really nice thing. If you have it on constant recycle or high recycle, as long as you purge your light stuff so you don't end up with a pressure problem, you're okay with a high recycle, and it's equal to a CSTR, simple equation, one that you all remember. Today's tutorial will help you remember it. So that's the equation you would normally use, because you've seen it before, the recycle ratio plus 1. The integral with respect to conversion, R over R plus 1, which is your feed in, because it's now your recycle, plus the 1 that you've added to it, remember, over is the integral of dxa over R. And that's straightforward second year notes. But now we've just changed it, and it certainly becomes a CSTR equation, which is a hell of a lot easier to deal with, and you can pretend that that's what it is. So the advantage of recycle is it's flexible, it can allow you to have perfect mix flow, and it can also have it as plug flow when you haven't got any mixing. The problems are there. If you've got large volumes of recycle, you've got problems with pumping, you've got problems with nasty materials. Overall, your avoidage is high, and if it's a homogeneous reaction, what the hell are you using a recycle for anyway? That's bottom line. So that really is a stupid but obvious statement. It's in all the textbooks. It's stupid and it's obvious, but it's in the textbooks, and you'll say, what does it mean? It means a homogeneous reaction doesn't need a catalyst, therefore it's in a pot. What's the point in it being anything else? Just remember, it's a batch reactor effectively if there's no mixing. A novel reactor that you've never seen before. You remember I said this morning about your little impeller with the top and the bottom, and now you've got the catalyst in the middle, and we've just spent $1,500 buying a box, a little basket on an impeller rod just like that, 1,500 quid. And it looks like a tea strainer. And it's the size of a tea strainer. I could have gone to the pound shop and got one and drilled a hole through it and stuck something on the top and the bottom and made it myself, had I but known that's what I was buying. It's set up so the basket and the catalyst in the pellet, that's a posh way of looking at it. You just imagine the basket with it just sat like a tea strainer, exactly the same. You put the tea in it and the catalyst is in there. Imagine now as you're stirring it, the reactants are coming into contact with the agitator, and that contact is making it mix. It's making the thermal effects diminish. It's doing everything, and it acts like it's a CSTR. In effect, it's a thoroughly mixed system. So the moment you've added everything in, it's mixed, and it's in, and it's mixed, it's reacted, and it's out. So it's acting as a thoroughly well mixed, and it says on there, continuous stirred tank catalytic reactor, or a stirred gas solid reactor. I'd be using it as a stirred gas solid reactor. I can't bring in a little basket to show you how unimpressive 1,500 quid buys you, because he's actually put it in the reactor. But if you just go home tonight and you've got a little thing that pinches together, or you go in the pound shop, look for a catalyst tea device, okay, because it's equivalent to making a cup of tea. So the equation simplifies into that equation, and you're all going, yeah. Well, when you come to the tutorial in a little while, you go, what did he say again? How does he get that? So, I'll say it, but there's no point, because you've got to do it yourself. Thoroughly believe in you doing some of the problems yourself so that you get the idea of the answers. So positive points, good back mixing, isothermality, mass transfer rate is now independent of throughput because everything's mixed and the catalyst comes to you. So where before we have it flowing past and away and around, the catalyst is whizzing around inside the reactor and the gas has got to go past the catalyst. It's no choice. So you've automatically reduced any influences there. Pellet geometry, well, the flow characteristics are not generally affected because they're moving around in this basket and everything's thoroughly mixed. What is effectively happening is not the catalyst is moving, but the flows are moving around the catalyst because you're stirring an agitator. Problem is, it's stirring. You've got a seal, it leaks. If it's at high pressure, you've got nasties and you've got a leak of something that might react with something like an electrical furnace or something that's dangerous and it might go pop. And also, because it's got moving parts, it does need lubrication, and I can vouch for the fact the biggest problem I've got is when this thing gets hot, the grease runs down the impeller and drips onto the catalyst and it kills your catalyst. It's a big problem on an old machine, which is why we just spent 1,500 quid on a new one. Strongly recommend for those of you who are doing design that this older textbook by Carberry, famous name, J.J. Carberry, 1976, you can look up things, but it's got other interesting bits on design and how to approach design problems. So I do recommend that. So if you've got your notes and it's in your notes now, just highlight it, because it is a good text. You'll find that as you go back another 20 years on that, to 1950s, there are textbooks that are written in words. This is for people like me who are hard of learning, okay? So I have trouble with engineering concepts sometimes when they put lots of squiggly D's in front of me. So fixed law and the rate of diffusion and the difference and the second order differential and so on. I'm going, what's he talking about now? He's talking about the rate of flux through the damn thing. I don't quite get that. The old books talk in words, so they actually describe the functions. You link the older book with a newer book, you get a better understanding. So I do recommend a couple of texts on chemical engineering, on reaction engineering from the 50s, which are in the library. You just need to look at an old textbook that's falling apart. And there are quite a few. I won't give you any names because you'll all go, we're not looking at that, it's old hat. When you come back and ask me separately, I'll tell you what they are. Okay, all of that is true. Now then, last concepts before you can have a go at the tutorial question. Here we go. I always struggle with this bit for the simple reason it's got concepts in it that you have to pull from different parts of the course. Remember what we said now, we've got three elements. Mass transport, we've got diffusion, and we've got the active site and the reaction itself. Remember the rate equation looking up there with its effectiveness and its voidage, its surface area and its bulk density and the concentration. Just focus on KCA. KCA. Then you've looked at the various things on the geometry that we looked at. We said, okay, well if we've got poor diffusion as a main problem, we reduce the length scale of the pellet to get around the poor diffusion. But we remembered that, in fact, the effectiveness was effectively proportional to 1 over NL, 1 over the TD modulus. That's what we said from 2 weeks ago, or even last week, sorry, 2 lectures. So now, when you look at the equation, you can see that in a slab geometry, we looked at a slab, remember before, H comes out as equal to A, which is the length scale, remember? And remember the bit that's in there with the fixed diffusivity and the top bit has the surface area. But if you focus and just simply remember that the K is on the top, when we looked at Thiele modulus, we had a particular equation which had the radius of the pore on the bottom and the diffusivity on the bottom. The effective diffusivity was on the bottom, and we had the radius on the top was the rate constant. It's the same equation, it's just described slightly differently. You've pulled out from the rate constant now the surface area of the catalyst and the density of the catalyst, but you're still over the diffusivity, so it's the same equation. So if you move around and play around with the equations and substitute in as substituted in there, you end up with the rate is equal to this equation, square root of the actual surface rate and the diffusivity times the square root of these parameters here. In effect, you're looking at the K observed is equal to CAB. So how did Dr. Garforth pull off that remarkable sleight of hand? He basically said, constant, 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 constant. KS, CA, two things that might change. KS should be a constant. I'm going to wrap everything into my K observe. So, it's my privilege to tell you that my supervisor, when I was doing a PhD and a postdoc, spent 6 years trying to beat that concept into me. I don't mean beat really, because we weren't allowed to do that, but it did feel like he bashed me over the head frequently. K observe. K observe. It means you can see me wandering up and down going, how am I going to try and get this concept across to you lot? K observe just means it's an average of everything that happens. You only get to measure something that is an average of everything that you as chemical engineers believe you've got a formula for. You haven't. You've got a formula for it, but you can't do naff all about it. You've got what you've got, and the catalyst behaves the way the catalyst does because of a certain set of circumstances that you do not control. You try to get the best catalyst, the best process, and set it up in the best way. That's what you do. But ultimately, when you measure the rate, when some idiot in a lab like me tests that catalyst, they get an answer, and it isn't what you like. You don't like that answer because it's 40% conversion and not 90%. This catalyst was the bee's knees. Why is that? That's because I'm measuring K observed, and I know what the conversion is of this thing from the bulk to what it is after it's been through the catalyst. And that K observed has all those parameters in it. It's got the surface reactant. We've done the Langmuir-Hinchelwood model. We're fine. We've got some idea of the diffusivity, and all we do is divide it by 10 to make it better. Whoa, that's really staggeringly good news. So now we can make a particle half the size or a tenth the size, and we've still got a bulk density and surface area. And some bright spark who did the tutorial not long ago said, Dr. Garfield, what's the limit of 1,000 meters squared for a catalyst? And I said, it's only the number of holes you can put in it before it falls apart. So you've got a limit on that bit as well. So that's got a limit on it that you really don't control because the chemist gives it to you and you try and adapt it. The bulk density is dependent upon, of course, how heavy your material is, and those two are linked. So then you've got the voidage, which you know you have a staggeringly formulaic way of doing that. It's either 0.4, 0.5 or 0.6. We'll approximate 0.5, so we'll use twice as much catalyst. That's the kind of limits you have, and that's why I measure that. And lots of people try to convince you they're modelling that and giving you that answer. You have to decide whether it's right or wrong. But that's the whole sum. So we now have all those equations pulled together. All that's happened is all the square root terms and everything else has been pulled into K observed. So we've just put K observed asterisk. All the constants in it. Right. It's commonly known that if you've got diffusivity effects and you've got catalytic surface reaction, if the diffusivity effects are significant, it'll halve the activation energy that you see. So the activation energy that you see, observe, measure, not calculate, but measure, is half that of the reaction. And the reason is, and if anybody taught you CRE properly, they should have told you that Arrhenius was around at the same time as somebody else, and they both came up with competing theories for temperature dependence of catalytic reactions. And when they did, they came up with one which was based on the number of molecules in a space banging into one another, so they had energy, and that was temperature dependent. And somebody else, Arrhenius, came up with, well, it's temperature dependent because it affects the rate. Of course, if you think about it, the number of molecules you've got in a space banging around actually is not too dissimilar from that of what's the rate, the number of molecules coming into contact with the surface and reacting away. Okay. Take it on board, look at the equation above. Diffusivity is therefore exponential with the activation energy for diffusion over RT, and the rate constant is the activation energy, or the E observed as the reaction, divided by RT. The two things come down with E observed equals E reaction over E reaction plus E diffusion. Therefore, you end up with an average value which is half the size. Bless you. So what does it all mean? Last slide. About 4 minutes to do something with it. So the whole course is represented on the slide. Today it does not feel like it. When you do the revision session before the exam, and I do the masterclass because you've read the notes and understood them a bit better, you will see how the whole course hangs on this one thing. You are the guys and girls doing the reactors. You're designing how much catalyst. That graph and where you are on that graph dictates whether you're completely useless, completely stuck and don't know how to improve it because you can't, or you're measuring exactly what you think you're doing. Unfortunately for you, there's only one that tells you exactly what you think you're doing, and it's that one, and it's the surface reaction. So when you're measuring the energetics, so if we look at the axes, log of the global rate at a fixed concentration over 1 over T, it's an Arrhenius plot. It's just a straightforward Arrhenius plot. So you've done some reactions, you've measured the conversions, and you've changed the temperature and measured the conversions again. So you've done your standard first year chemical reaction engineering kinetic experiment where you've done the rate, you've held the conditions the same, and you've changed the temperature. And then you've done your Arrhenius and you've got your negative line plot, the gradient of which gives you the E observed. Not longer do you say E activation, you now start to say E observed. So, but it's of the reaction. That's what you should get. We've now got the theory, or the few formulas that all you really need to know is the diffusion is temperature dependent and the rate is temperature dependent, so when you have the two together, we assume it's halved. Of course, you can get somewhere in between, but it means the slope of your curve is less than you think. Typical chemical bond breaking is 60 to 80 kilojoules per mole. Typical. It can be higher, but it's typical. You get a value lower than that, you might be in the diffusion range. So when you get 20 to 40, you might have made an error. The guy doing the test or the girl doing the test might be a klutz and it might be wrong, it might be out, might be to retest it. But if it's lower than 60 kilojoules per mole and going towards 10 kilojoules per mole, you're going to start thinking it's diffusion problems. So what do? You tell the guy or the girl who's doing the testing to reduce the particle size. Do it again. What happened? Did you get a different number? No. Okay, well then it's likely to be moving into this diffusion-controlled region. Then you get the poor unhappy circumstance of the catalyst that you gave to the lab, and the lab test it, and they go, I've changed the temperature loads of times, but I get no difference in my activation energy. I've got a straight line. Answers on a postcard. It's obviously down to mass transfer because you're not getting concentration out of the bulk to the active site because the reaction's not taking place. Because if the reaction was taking place and if diffusivity was active but not overriding completely, you'd have some kind of change. So look at the graph again now as I would look at the graph. Try anyway, just for the last thing before we finish. Because you're going to get to test it when you do the tutorial question. So, a straight line, no change with temperature on your global rate, and your activation energy is coming out with the slope as 0. Mass transport limited. I can't possibly be getting anything to the catalyst surface. Nothing at all. Because nothing's changing my rate. Nothing's doing anything when I change the temperature. Now we all know Arrhenius' law, we know that's not possible. But it is, so we've set it up wrong and we've got to do something about it. At this end, we've got 60 to 80 kilojoules per mole, so we know we've got a chemical reaction. We know that 3/4 of all reactions, remember, are surface reaction limited, so it's doing what it says on the tin. Everything is on the surface, it's working as it should, and we're getting a reliable number for our activation energy, which means we've got reliable rate data, which means we can scale on the rate data. The one in the middle, we have to manipulate, because we've got two effects. We've got the rate and we've got diffusion. Two effects, rate and diffusion. Unfortunately, it's never quite as easy as that graph. Okay? And that graph just simply says there's a clear difference. Of course, there are grey boundary areas and there's grey areas on it all. But it's a pretty good summary of what the course is about. Now, I could have started the course with that. We haven't finished the course, of course, but it's just the course is represented in surface reaction, Langmuir-Hinshelwood kinetics, modeling the reaction kinetics. Diffusion, how do we allow for diffusion? Well, we must know it's there. And then finally mass transport, well, we're stuffed, we better redesign the whole thing because it's not working properly. Okay? So that used to be a brilliant exam question until everybody started regurgitating the same slide but without any understanding. So when asked to explain it, they shot themselves in the foot. So it is a really good summary of where you're at with the course. You might not see it now, but hopefully you will see the individual steps. We want to always be, last time, always be in that part. We want to always say that the people like me who publish the literature that have the problems with the reactors, like you see there, have got it right, and they've sorted it, or they've told us that they've got a temperature issue, and then we're moving accurately on that scale. Anything else, if we get a very low number, when we test it, we've got diffusion,